I want to start by telling you honestly what I think terrifying actually means when it gets attached to a scientific discovery. Because I've found across every one of these conversations that the word usually promises more drama than the physics itself, once explained clearly, actually delivers. What astronomers have found is not a monster lurking in our galaxy waiting to threaten Earth. It's something considerably stranger and, I think, more genuinely fascinating. A source somewhere in the Milky Way capable of accelerating individual protons to energies so extreme that nothing built by any civilization on Earth, including every particle accelerator physicists have ever constructed, comes remotely close to matching it. Let me start with the number itself because I want you to understand exactly how extreme this energy scale actually is, using comparisons that make the scale genuinely graspable rather than simply abstract. Physicists measure the energy of individual subatomic particles using a unit called the electron volt, defined as the energy an electron gains when accelerated through an electric potential difference of 1 volt. It's an extraordinarily small unit at the scale of everyday experience, but it's the natural currency for describing the energies involved in particle physics, the same unit I used constantly throughout my own career working with nuclear reactions and particle interactions. CERN's Large Hadron Collider, the largest and most powerful particle accelerator human civilization has ever built, an underground ring, 17 miles in circumference, requiring an entire international collaboration and billions of dollars to construct and operate, accelerates protons to energies of approximately 6.8 trillion electron volts per beam, or roughly 13.6 trillion electron volts, in head-on collisions between two counter-rotating beams. This is already an extraordinary achievement, the product of decades of engineering refinement, representing the absolute frontier of what human technology can currently accomplish in accelerating particles. The object astronomers have recently and conclusively identified within our own galaxy accelerates individual protons to energies exceeding 1 quadrillion electron volts, what physicists call a peta-electron volt, or PeV for short. I want you to sit with the scale of that comparison directly. 1 quadrillion is 1,000 trillion. The single astrophysical source, sitting somewhere within our own galaxy, is accelerating individual particles to energies roughly 100 times higher than the absolute maximum the Large Hadron Collider, humanity's most powerful and expensive scientific instrument, can achieve using nothing but the raw physics of some extraordinarily violent astrophysical process entirely without human intervention or design. I want to walk through how astronomers actually identified this source, because the detective work involved genuinely deserves to be understood in some detail, rather than simply asserted as an announced conclusion. The particles I'm describing, these extraordinarily high-energy protons, are part of a broader category of particles called cosmic rays, which have been detected reaching Earth's atmosphere for over a century, first identified through balloon-based experiments conducted by physicist Victor Hess in 1912. Cosmic rays are overwhelmingly protons and atomic nuclei arriving at Earth from somewhere out in space, having been accelerated to extraordinarily high energies by some astrophysical process before beginning their journey toward us. Physicists have understood the basic existence of cosmic rays and their generally extreme energies for over a century now. What has remained frustratingly elusive for decades of dedicated research is identifying the specific astrophysical sources responsible for accelerating the highest energy cosmic rays, the ones reaching energies in the PeV range and above, sometimes referred to collectively as the problem of pevatrons, a deliberately playful term echoing the way particle accelerators like Fermilab's old Tevatron were named for the energy scale they achieved. Applied here to whatever natural astrophysical process manages to accelerate particles to comparable or greater energies without any human engineering involved at all. The difficulty in identifying specific Tevatron sources comes from a fundamental limitation in how cosmic rays themselves can be tracked. Because cosmic rays are electrically charged particles, protons carry positive charge. Their trajectories get bent and scrambled by the magnetic fields permeating interstellar space as they travel toward Earth, meaning that by the time a cosmic ray proton actually arrives and gets detected, its original direction of travel has been essentially randomized, erasing any direct information about which specific astrophysical object originally accelerated it. You can detect that extremely high-energy cosmic rays exist and are arriving at Earth, but you cannot simply trace their arrival direction backward to identify their source the way you could with an ordinary beam of light. This is where a different indirect detection strategy becomes essential, one that relies on gamma rays rather than the cosmic ray protons themselves. When a high-energy cosmic ray proton, freshly accelerated near its source, happens to collide with other matter still in the vicinity, ordinary interstellar gas, for instance, that collision can produce gamma rays, the most energetic form of electromagnetic radiation, through a well-understood particle physics process. Crucially, unlike the charged cosmic ray protons themselves, gamma rays are electrically neutral, meaning their paths through space aren't bent by interstellar magnetic fields the way charged particles are. A gamma ray once produced travels in a straight line directly back to its point of origin, meaning that if astronomers can detect gamma rays with energies consistent with having been produced by PeV-scale proton collisions and can trace those gamma rays back to a specific point in the sky, they found strong indirect evidence for exactly the kind of Tevatron source they're searching for. This is precisely the detection strategy that led to the recent identification of the specific source, now catalogued as LHAASO J1912+1014u, using a massive cosmic ray and gamma ray observatory called LHAASO, the Large High Altitude Air Shower Observatory, located at high altitude in Sichuan, China, specifically designed and built to detect exactly this kind of extremely high-energy gamma ray signal, along with additional confirming observations using NASA's Fermi Gamma Ray Space Telescope, which identified a corresponding excess of somewhat lower-energy gamma rays from the same specific location in the sky, providing independent, multi-wavelength confirmation that something at that precise location is indeed accelerating particles to PeV-scale energies. I want to be honest about what remains genuinely uncertain in this discovery, because I think intellectual honesty matters more here than simply celebrating an impressive-sounding number. Astronomers have conclusively identified a location in our galaxy responsible for accelerating protons to PeV-scale energies, confirmed through multiple independent gamma ray observations at different energy ranges, which represents a genuinely significant achievement in the decades-long search for identifiable Tevatron sources. What remains less certain, at least as of the most recent published analysis, is the precise physical nature of the object or region actually responsible for the acceleration, whether it's associated with the remnant of a supernova explosion, a specific and well-studied category of astrophysical object, long suspected of being capable of this kind of extreme particle acceleration, or whether it might be associated with some other extreme astrophysical environment, such as a pulsar wind nebula. the highly energetic magnetized environment surrounding a rapidly rotating neutron star. I want to explain why supernova remnants specifically have long been considered leading candidates for cosmic ray acceleration, because I think the underlying physics connects directly to concepts I've discussed in earlier conversations about the extreme conditions surrounding stellar collapse. When a massive star reaches the end of its life and explodes as a supernova, the explosion drives an enormously energetic shockwave outward into the surrounding interstellar medium, expanding at velocities that can reach a meaningful fraction of the speed of light in the earliest phases after the explosion. Charged particles caught up in the turbulent, magnetized environment surrounding this expanding shockwave can be accelerated through a process called diffusive shock acceleration, essentially bouncing back and forth repeatedly across the shockwave boundary, gaining a small additional increment of energy with each crossing in a process that, given enough time and a sufficiently strong, sufficiently extended shockwave, can plausibly accelerate individual particles up to and potentially beyond PeV scale energies, before the particles eventually escape the shockwave region entirely and begin their long journey through interstellar space, eventually arriving some small fraction of them at Earth's own atmosphere as the extremely high-energy cosmic rays physicists have been detecting and puzzling over for over a century. I find myself genuinely moved by this discovery in a way that I think deserves to be explained honestly rather than dismissed as simple scientific enthusiasm. Throughout my own career, I spent an enormous amount of effort thinking carefully about how to accelerate charged particles to extreme energies and how to extract useful, controllable energy from nuclear processes involving those particles, work that culminated in the most consequential and troubling application of my career, in the design of weapons capable of releasing nuclear energy on a scale that dwarfed anything achieved by previous human technology. And yet here, within our own galaxy, sits a naturally occurring astrophysical process requiring no human design or intervention whatsoever, casually accelerating individual protons to energies vastly exceeding anything the most sophisticated human engineering, applying billions of dollars and decades of dedicated effort, has ever managed to achieve. I want to address directly whether this discovery represents any kind of danger to Earth, because I think this is precisely the question a title using the word terrifying implicitly, if somewhat misleadingly, invites. And I want to give you an honest, carefully reasoned answer rather than either dismissing the question entirely or exaggerating a risk that the physics doesn't actually support. The specific cosmic rays this source produces, and cosmic rays in general, arriving at Earth from sources throughout the galaxy, do interact with Earth's atmosphere continuously, and have done so throughout the entire multi-billion-year history of our planet, including throughout the entire span of human civilization and long before it. Earth's atmosphere, combined with our planet's magnetic field, provides substantial protective shielding against the vast majority of this incoming cosmic ray flux, and the specific rate at which extremely high-energy cosmic ray particles, at PeV scale energies and above, actually reach Earth's surface is, in absolute terms, quite low, precisely because particles at these extreme energies are relatively rare compared to the much larger flux of lower energy cosmic rays constantly bombarding our planet. The discovery of this specific pevotron source doesn't represent some sudden new threat to Earth. It represents astronomers successfully identifying for the first time with real confidence one specific astrophysical location responsible for producing particles at energies that have already been arriving at Earth in small but measurable quantities for the entire history of our planet's existence, without this ongoing background cosmic ray flux posing any kind of acute danger to life on Earth. protected as we are by our atmosphere and magnetic field. What I find genuinely exciting about this discovery, rather than frightening in any literal sense, is what it teaches physicists about the extreme astrophysical environments capable of accelerating particles to energies our own most sophisticated technology cannot match. Understanding precisely how nature achieves this kind of extreme particle acceleration, whether through the specific mechanism of supernova remnant shock waves or through some other extreme astrophysical process associated with pulsar wind nebulae or other exotic objects, connects directly to some of the deepest open questions in astrophysics, including the broader question of where the very highest energy cosmic rays ever detected, reaching energies even beyond the PeV scale this particular source demonstrates, ultimately originate from a question that has remained genuinely unresolved despite over a century of dedicated observational effort since Victor Hess's original 1912 discovery. I want to close by returning to the framing this title suggests, because I think, as with several of our other conversations, the honest answer reframes the question in a way I find considerably more interesting than the more sensational version. Scientists have not discovered something terrifying lurking within the Milky Way in the sense of some newly emerged threat to Earth or to human civilization. What they've discovered through a genuinely impressive combination of multi-wavelength gamma-ray astronomy and years of careful patient observational work is a natural astrophysical accelerator, sitting somewhere within our own galaxy, casually outperforming every particle accelerator human engineering has ever managed to construct by a factor of roughly 100, using nothing but the raw physics of an extreme astrophysical environment, quietly operating, entirely indifferent to human observation for as long as it has existed. I think there's something genuinely humbling in that fact, considered honestly rather than sensationally, and I think it connects to something I've returned to throughout so many of these conversations, reflecting on physics from wherever this reflection is actually coming from. Human beings, for all the genuine ingenuity and effort we've invested in building instruments like the Large Hadron Collider, remain, in this specific and very real sense, considerably outmatched by processes the universe itself carries out casually as a simple, if extreme, consequence of stellar physics operating exactly according to the same fundamental laws I spent my entire career trying to understand. That's not a threat. It's a reminder of how much extraordinary physics the universe conducts constantly, all around us, entirely independent of anything human civilization has ever managed to build, waiting, as it always has, for careful, patient observation to finally reveal exactly what's actually happening out there.